Welcome to a fascinating journey through the lesser-known corners of the periodic table, the Lanthanides and Actinides series. These two groups of elements, often tucked away at the bottom of the periodic chart, play crucial roles in modern technology, energy, and even medicine. Today, we'll explore what makes these elements unique, why they're separated from the main table, and how their properties have shaped scientific discovery. Get ready to uncover the secrets of these hidden elements and understand their significance in our daily lives and the world around us. If you've ever glanced at a periodic table, you might have noticed two rows set apart from the main body. These are the lanthanides and actinides. Their placement isn't random, it's a clever way to keep the table compact while highlighting their unique electron configurations. The lanthanides occupy atomic numbers 57 to 71, while the actinides span 89 to 103. This separation helps chemists and students focus on their special properties without crowding the main table, making the periodic chart both practical and informative. Let's start with the lanthanides. These are a group of 15 metallic elements beginning with lanthanum and ending with lutetium. Known for their shiny silvery appearance, lanthanides are sometimes called the rare earth elements, though many are more common than you might think. Their unique electron arrangements give them fascinating magnetic and optical properties, making them vital in high-tech industries. From powerful magnets to color televisions, lanthanides are quietly powering much of our modern world. You might be surprised to learn just how often you encounter lanthanides in daily life. These elements are essential in the production of strong permanent magnets, which are used in everything from headphones to wind turbines. Their unique optical properties also make them crucial for color displays in TVs and smartphones. Even energy-efficient light bulbs and lasers rely on lanthanides. Without these elements, many of the devices we take for granted would simply not exist. Chemically, lanthanides are known for their similar behaviors. They typically form +3 ions and have high reactivity, especially with water and air. This similarity makes them challenging to separate from one another, which is why extracting pure lanthanides requires advanced techniques. Their chemistry also leads to interesting compounds with vibrant colors, often used in glassmaking and ceramics. Understanding their chemical nature helps scientists design new materials for cutting-edge applications. Extracting lanthanides from ores is no easy task, because these elements are chemically similar. Separating them requires complex processes like solvent extraction and ion exchange techniques. Mining for lanthanides often takes place in specific regions, such as China, which dominates global production. The extraction process can be energy-intensive and raises environmental concerns, making sustainable practices increasingly important in the industry. Neodymium is one of the most famous lanthanides, thanks to its role in making powerful magnets. These magnets are found in electric motors, wind turbines, and even headphones. Neodymium's unique magnetic properties make it invaluable for green technologies and miniaturized electronics. Its discovery and widespread use have revolutionized how we generate and use energy, making it a true star among the lanthanides. Europium is another standout lanthanide, best known for its role in producing the red color in television and computer screens. Its compounds are used in phosphors, which emit bright red light when excited. Europium's unique luminescent properties have made it essential in display technology, anti-counterfeiting measures, and even in euro banknotes to prevent forgery. Cerium is the most abundant of the lanthanides and has a wide range of uses. It's a key component in catalytic converters, which help reduce car emissions. Cerium oxide is also used in glass polishing and as a catalyst in self-cleaning ovens. Its ability to switch between oxidation states makes it incredibly versatile in industrial applications. Lanthanides aren't just for gadgets and industry, they're also making waves in medicine. Gadolinium, for example, is widely used as a contrast agent in MRI scans, helping doctors get clearer images of the body. Research is ongoing into new medical uses for other lanthanides, from cancer treatments to advanced imaging techniques. Their unique properties are opening new frontiers in healthcare. Now let's turn our attention to the actinides. This series includes 15 elements, starting with actinium and ending with lawrencium. Actinides are best known for their radioactivity, with some, like uranium and plutonium, playing central roles in nuclear energy and weaponry. Their unique nuclear properties make them both powerful and, in some cases, dangerous, shaping the course of history and technology. Radioactivity is the defining feature of most actinides. These elements have unstable nuclei that release energy in the form of radiation. This property is harnessed in nuclear reactors to generate electricity, but it also requires careful handling and storage to prevent environmental contamination. Understanding radioactivity is key to using actinides safely and effectively. Uranium is perhaps the most famous actinide, known for its use as fuel in nuclear power plants and in the creation of atomic bombs. Its ability to undergo fission, splitting into smaller atoms and releasing enormous energy, has made it a cornerstone of both energy production and military technology. Managing uranium safely is a major focus for scientists and policymakers worldwide. Plutonium is another actinide with a dramatic history. It's used in nuclear weapons and as a fuel in some types of nuclear reactors. Plutonium's radioactivity and toxicity require extreme caution in handling and storage. Despite its dangers, it has played a pivotal role in scientific research and energy generation. Thorium is gaining attention as a potential alternative to uranium in nuclear reactors. It's more abundant and produces less long-lived radioactive waste. Some countries are investing in thorium reactor research, hoping to develop safer and more sustainable nuclear energy solutions for the future. Actinides aren't just about energy and weapons, they also have important medical uses. For example, americium is used in some types of cancer treatment and in smoke detectors. Research continues into how actinides can be safely harnessed for medical imaging and targeted therapies, offering hope for new breakthroughs in healthcare. Extracting actinides from natural sources is a complex and often hazardous process. Uranium and thorium are mined from the earth, while other actinides are produced in nuclear reactors. The extraction and refinement processes must be carefully managed to protect workers and the environment from radioactive contamination. One of the biggest challenges with actinides is managing the radioactive waste they produce. Spent nuclear fuel contains long-lived actinides that must be stored securely for thousands of years. Scientists are researching new ways to recycle or neutralize this waste, aiming to make nuclear energy safer and more sustainable for future generations. Actinide series includes several transuranic elements, those with atomic numbers greater than uranium. These elements, such as neptunium and americium, are mostly synthetic and produced in laboratories or nuclear reactors. They have specialized uses in research, industry, and even space exploration, despite their rarity and radioactivity. While both lanthanides and actinides share similar positions on the periodic table, they have distinct differences. Lanthanides are mostly stable and non-radioactive, while actinides are known for their radioactivity. Their uses also differ. Lanthanides are vital for electronics and optics, while actinides are central to nuclear energy and medicine. Understanding these differences helps us appreciate the diversity of elements in our world. You might wonder why lanthanides and actinides are placed separately from the main periodic table. The answer lies in their electron configurations, which are unique and don't fit neatly into the main table's structure. By placing them below, chemists can maintain the table's shape and highlight the similarities within each series, making the chart easier to read and understand. Both the lanthanides and actinides are known as the F-block elements. This refers to the type of atomic orbital that their electrons fill. The F-block is characterized by the gradual filling of the 4f and 5f orbitals, which gives these elements their unique chemical and physical properties. Understanding the F-block helps chemists predict the behavior of these elements in reactions and materials. One of the most striking features of lanthanides and actinides is the colorful compounds they form. Lanthanide ions, in particular, produce vivid colors when dissolved in solutions or incorporated into crystals. These colors are used in everything from decorative glass to advanced lasers, adding both beauty and function to modern technology. Lanthanides are famous for their magnetic properties. Elements like neodymium and samarium are used to make some of the strongest permanent magnets known. These magnets are essential in electric vehicles, wind turbines, and computer hard drives, driving innovation in clean energy and information technology. Some lanthanides like europium and terbium are prized for their luminescent properties. They emit bright colors when exposed to certain types of energy, making them ideal for use in lighting, television screens, and even anti-counterfeiting inks. Their glow is not just beautiful, it's also highly practical. Actinides like uranium and plutonium are the backbone of nuclear power generation. Their ability to undergo fission releases vast amounts of energy, which is harnessed to produce electricity. Nuclear power is a major source of low-carbon energy worldwide, but it also comes with challenges related to safety and waste management. Some actinides like plutonium-238 are used as power sources for spacecraft. Radioisotope thermoelectric generators, RTGs, convert the heat from radioactive decay into electricity, powering missions to distant planets and beyond. Without actinides, many deep space missions would be impossible. Mining and processing both lanthanides and actinides can have significant environmental impacts. These include habitat destruction, water pollution, and the generation of radioactive waste. As demand for these elements grows, developing cleaner and more sustainable extraction methods is becoming increasingly important. The supply of lanthanides and actinides is a global issue. Many countries rely on imports for these critical materials, with China dominating the lanthanide market. This concentration of supply can lead to geopolitical tensions and highlights the need for diversified and secure sources. Recycling lanthanides and actinides from used products is an emerging field. Recovering these elements from electronic waste and spent nuclear fuel can reduce environmental impact and secure supply. Innovative recycling technologies are being developed to make this process more efficient and cost-effective. Both lanthanides and actinides are central to the future of clean energy. Lanthanides enable efficient wind turbines and electric vehicles, while actinides power nuclear reactors. Continued research and innovation in these fields could help reduce our reliance on fossil fuels and combat climate change. The unique properties of lanthanides and actinides are driving breakthroughs in medicine. From advanced imaging agents to targeted cancer therapies, these elements are helping doctors diagnose and treat diseases more effectively. Ongoing research promises even more medical innovations in the years ahead. Studying lanthanides and actinides isn't easy. Their similar chemical properties, radioactivity, and scarcity make laboratory work challenging. Scientists use advanced techniques and specialized equipment to safely handle and analyze these elements, pushing the boundaries of our knowledge. The discovery of lanthanides and actinides spans centuries and continents. Early chemists struggled to isolate these elements due to their similarities. The actinides especially were discovered in the 20th century, often as byproducts of nuclear research. Their stories are filled with scientific curiosity, competition, and innovation. Many lanthanides and actinides are named after places, scientists, or mythological figures. For example, Europium is named after Europe and Cerium honors Marie and Pierre Curie. These names reflect the global and historical impact of their discovery and use. The inclusion of lanthanides and actinides changed the way we view the periodic table. Their discovery led to the expansion of the table and a deeper understanding of atomic structure. Today, the periodic table continues to evolve as new elements are discovered and classified. Handling lanthanides and actinides requires strict safety protocols, especially for radioactive actinides. Laboratories use shielding, remote handling tools, and protective gear to minimize exposure. Proper training and regulations are essential to protect both workers and the environment. The search for new lanthanides and actinides continues. Scientists are synthesizing new elements in laboratories, pushing the boundaries of the periodic table. Each discovery brings new insights into atomic structure and the forces that hold matter together. Learning about lanthanides and actinides helps students understand the complexity and beauty of chemistry. These elements illustrate key concepts in atomic theory, periodic trends, and the relationship between structure and function. Their study inspires curiosity and innovation in future scientists. Though they may seem obscure, lanthanides and actinides touch our lives every day. From the screens we watch to the energy that powers our homes, these elements are woven into the fabric of modern society. Their continued study and responsible use will shape the technologies of tomorrow. As demand for lanthanides and actinides grows, sustainability becomes crucial. Researchers are developing greener extraction methods, recycling programs, and alternative materials to reduce environmental impact. These efforts aim to balance technological progress with environmental responsibility. The study and use of lanthanides and actinides require international cooperation. Scientists, governments, and industries work together to ensure safe handling, fair trade, and shared research. Global collaboration is key to unlocking the full potential of these remarkable elements. Raising public awareness about lanthanides and actinides is important for informed decision-making. Understanding their benefits and risks helps communities support responsible policies and sustainable practices. Education and outreach can bridge the gap between science and society. The future of lanthanides and actinides is full of promise and challenge. As technology advances, new uses and discoveries will emerge. By balancing innovation with responsibility, we can harness the power of these elements to build a brighter, more sustainable world. In summary, the Lanthanides and Actinides series are more than just footnotes in the periodic table. They are essential to modern life, driving advances in technology, energy, medicine, and beyond. By understanding their properties, uses, and challenges, we gain a deeper appreciation for the complexity of the natural world and our role in shaping its future.